Okay, hello everyone. In the last class, we have looked at the EK relation for periodically arranged potential, meaning periodic potential. Okay, so and we have anyway before that we have looked at single atom to crystal. Okay, and the periodic potential primarily arises from the nucleus, electrostatic potential, right? We have periodically arranged atoms. Okay, and we have seen that when atoms are close by, okay, then we have overlap of overlap of wave functions, and because of that, there is splitting in the energy levels. We have seen formation of bonding and anti-bonding. So this was a picture for simple hydrogen atom, meaning hydrogen atom forming hydrogen molecule. And then we extended this idea and seen like what happens for silicon. Okay, yeah, this is kind of thought experiment, very intuitive understanding that initially energy levels will split and eventually they will merge and they will hybridize, and the atomic spacing of silicon is such that we have this conduction and valence bands. Okay, and we have seen that the core electrons, do not split much because their orbital overlap do not interfere significantly. So this is a phenomena primarily taking place with the outermost shell electrons, right? Yeah. Anyway, so these are the bands, meaning allowed energy level, right? Within the band, there are certain allowed energy level. I mentioned that there will be some distribution. It is not that, they are linear, okay? Okay, so later on, not today, we will look into that. So these are called density of states. Okay, maybe in the next lecture we'll see how to derive density of states. Okay, yeah. So this is an important thing. So we have bandwidth, and band gap. So within a band, there is a distribution of energy levels. Okay, yeah. So now, so this is a periodic potential for a single atom, and we have seen, okay, now if we have atomic chain, we have considered 1D atomic chain for simplicity. So still this is a bit complicated because there we have 1 by R dependence. So we simplified it. There was another thing. So essentially our target is to find energy as a function of K. And we know how to get it done using or solving time independent Schrodinger equation. So you have solved it for free particle for infinite potential barrier. But here the thing is we have, periodically arranged infinite number of atoms, right? Then how do you solve? So essentially what we need is a trial wave function, which is given by Bloch. So Bloch essentially said that the wave function will take this functional form, which will be periodic with the periodicity of this atom. Okay, and alongside, this is modulated. It is like analogous to amplitude modulated signal. Okay, and also we mentioned that this atom and this atom, they are identical. Okay, so we have periodic boundary condition. If you use it, then we are almost done. Okay. Okay, so we need to solve this Schrodinger equation to find E as a function of K. So previously we have seen continuity of wave function and its first derivative. And here we will use this boundary condition in addition, okay, to solve this equation. But still this was a bit more complicated. So we simplified it, assuming rectangular finite potential well, because equations already you have already solved for single potential well or barrier. So this is not that complicated. So again, so there were two regions, region A, 0 to A and 0 to B. We solve it separately. So this was for 0 to A and this is for 0 to B. So this is the equation and its solution for this region, and this was the case for this. Okay. Now we have these two equations and 4 unknowns. So the way we could solve it by considering the continuity of wave function at x equals to 0 and x equals to this point A. Okay, the moment I'm saying point A, that means x equals to A, that means it is x equals to minus B because of the periodic boundary condition. So also we use that. Okay, so that was the point number 1, and point number 2 is the first derivative. These are simple differential equation. If you spend some time, maybe 20-30 minutes or whatever, then you should be able to solve it. It's not a big deal. There is no big rocket science here. 4 simple differential equations you need to solve. Okay, So now we have 4 equations or 4 unknowns. Okay, then we can solve for it. Solve for it meaning we can eliminate these coefficients. If you eliminate these coefficients, what do you get? So you get, note that within this alpha or beta, what do we have? We have expression of energy, and here we club this using the periodic boundary condition. We get the information of k. That means when you solve, you can get E versus k relation. Okay, yeah, this is a repetition. So this is some sort of E versus k relation we get for this simple system. So now the thing is we need to solve for it. Okay, so this is like one function, one of the functions, say sine. There's another function, right? You remember in the last class we have seen how to solve it. Okay, for example, we gave this example. So this is function of energy. Okay, because within this constant we have energy, so this is function of energy. So if you plot it, it will look like that. Okay, so this is E. So generally we plot f versus x, but here we have flipped. We are plotting E versus x, so that we in the vertical line we have E, so that we can get E versus k. This is fine. You can just plot it, okay, or you can assume this function will look like that. So solution will lie within this region, because this is here we have the cost for different values of k. No matter what value you take, the solution will be plus minus 1. So that's why we have plus minus 1, and I have seen how to take the mapping. So here plus 1 corresponds k equals to 0. So this is mapped here, and minus 1 means k equals to what? Pi, right? So anyway, here pi over a plus b. So it is mapped here and in between. Okay, so if you connect them, then you get this. So whatever we have for positive k, you will get the same thing for the negative k, because there's a cos function. So cos plus x and cos minus x are same, right? So you get this first band. Similarly, you get the second band, and so on and so forth. Okay, so here that means you find dispersion. Okay, the value of E varies. Okay, it depends on a k. Okay, and very important, there are certain energy levels where we don't have any allowed energy level. We don't have any allowed value of E. Okay, so this was a discussion. So this is what we have, the so-called EK dispersion. Okay, and also I mentioned that near this band edge, okay, either rho zone or k equals to 0, we can use this approximate relation. We can assume that this is parabolic. I mean, this is kind of evident if it is if k is small. So in that region, it will be parabolic, because you can expand any function in terms of series of x, right? It is not a linear, that is obvious. So the next one is k square. Okay, so it is reasonable to have this. Okay, and then probably I briefly said this, and we ended that discussion. So now we'll start with this. Any question here? Any question? Yeah.
When we do frequency transformation, we can do algebraic. So can we solve this differential equation algebraic form?
Yeah. You need to solve this algebra. Right? You have 4 equations. You have 4 equations, and you need to eliminate the 4 coefficients. That you do with simple algebra. That's what I'm saying. The solutions are algebra. Differential equations are there from the Schrodinger. You have differential equation. The trial solution is like a sine kx, b sine ky, sorry, b sine b cos kx, like that.
So, that is there, but in Laplace transformation, we do solve the differential.
Yeah. It doesn't matter how you solve. You can use any technique to solve it. That's fine. You can do any technique. You can solve it also numerically. Okay. Okay. So now, yeah, we'll start with this. Let's consider weak electron. Sorry, let's consider almost or nearly free electron under weak periodic potential. Okay, so because this will again give us same picture. So previously we have solved Schrodinger, and which was the chronic penning model. Now we want to understand that without solving, because Maybe that is more intuitive. Okay. So essentially what we need is a periodic potential. That is because you can't get rid of that because our atoms are periodic. Okay. But now, and also you have solved equations for free particle. You know that solution, right? So let's combine this nearly because it is still under periodic potential. So that is not completely free, but almost free electrons under weak periodic potential. Okay. So if it is like free particle, free electron, do you agree? This would be the dispersion, E proportional to K square. Okay. Is it okay? Right? There is, I mean, this is continuous. So all energy levels are allowed. Okay, so from the previous understanding, we just borrowed this concept that at the Brougham zone boundaries, gap opens because that we have seen, and also intuitively you have seen that energy band split. Okay, just we will use it. Okay, so this green parabolic curve is what we have for the free electrons. Okay, now where will we have that gap opening? Near Brougham zone. Okay, that's why I kept it slightly. Okay, I bend it slightly upward. Here bending will be other way around. Do you agree this or not? So this is how your energy will be modified. Because it is like a free electron, right? But you are getting this small, I mean, you are having this gap because of that periodic potential. Is this intuitive? We are not solving anything, just we are borrowing this concept that we have opening up gaps at Brougham zone. That's all. Is this okay? Small, so everywhere. Okay. Okay. Now, so as you know, like this is 1D periodic potential, right? So if you do the Fourier transform, it will still be 1D and periodic, right? So that means now this is an extended Brougham zone. That's what it looks like. So now 0 to pi by pi over, I mean, a plus b, and so we will have repetition, right, in the K space. Because if you remember, like if you have periodic potential, okay, periodic discrete signal, when you do the Fourier transform, what do you get? Periodic and discrete, right? So we also get same thing. So K space is periodic. If it is periodic, why to bother with this? So the question is, instead of going throughout this entire, I mean, K space, can we use the symmetry? That symmetry is, you remember, two atoms are identical, A and B. Can we use it and redefine E versus K? Is this question clear? Is this point clear? Maybe it will be clear soon. Okay, so here, what I've shown, like E varies, right? It can be plus minus because, I mean, there's not E. So here, this function. Okay, because previously you have seen that, right? That cos k a, which can vary plus 1, minus 1. Remember? Previously there was that functional form, right? F of E, right? So k equals to 0, it was 1. K equals to pi, it is minus 1. K equals to 2 pi, again plus 1. Okay. Okay, that means, okay, how do you map from here to here? This first band will just directly be copied because here the range is pi over, I mean, the range is same. Fine, no issues. Now look at this graph. So this is the point when it is minus 1, right? The value is minus 1. Okay, so this is the point when it is minus 1. Okay, and this is the one when it is plus 1, and this is the one when it is plus 1. Sorry? Same. Both are same. So here I'm allowing it to run throughout the entire K space. Now my point is, after the Fourier transform, it is periodic. Periodic meaning, so here see, I mean, so this point and this point, they are identical. So whenever we have this point, can I shift this point here? Because they are identical. Okay. So now, so this point, so which is taking minus 1. You remember that cos Ka thing came, right, in the chronic Penny solution. So this point is minus 1. So this point will be mapped here. So what I'm saying is this pi by a, pi divided by a plus b is same as minus pi divided by a plus b. Do you agree or not? Simple cos, use your cos function, right? So now imagine a point here. So this point will be mapped here. E will not be changed. So whatever E we will have, we have. So whatever K we have, we can map it here because they're identical. Same here. So this point will be mapped here. That means all points in between will be mapped like that. Okay. Are you able to follow?
Sir, what's the difference between positive K and negative K?
So yeah, that's what I'm explaining. So this is the difference, whatever you can see between positive K and negative K. So here we are saying that it is extended, right? So a cos function, okay, whatever it varies, say from plus pi to plus 2 pi. Variation of a cos function from pi to 2 pi is same as variation of the same cos function from minus pi to minus 2 pi. That's what I mean. So wherever, I mean, so this point is essentially mapped here. X, I'm not changing E, I'm changing X. So this point, I'm saying this point is same as this point. So I am taking this point from here to here. Is it okay? Same, this point and this point, they are identical. So instead of showing it here, I just show it here. Sorry, instead of showing it here, I just show it here. Here meaning this point. So this is 2 pi effectively, and this is 0. 0 and 2 pi same, right? So instead of showing this point here, I can flip it and show it here. Is it okay? Do you agree? And you can do the same for all other points. Then it will look like that. You just connect it. Meaning essentially it will look like mirrored image here. So, sorry, not mirrored image, just shifted, okay? As shown here. Is it clear? Because this is very important. Okay?
Like, why are we shifting the negative space?
Yeah, the same. So cos pi meaning cos minus pi, right? That exactly what. Instead of showing this point here, I can show it here because x-axis is same. Because it is periodic. You can do it because it is periodic. We are exploiting the periodicity. Instead of showing the entire Brougham zone, which looks odd and bad, we are trying to make it concise. Is it okay? We are just trying to, I'm trying to tell you cos pi is same as cos minus pi.
Variation is for cosine is what?
So previously, so cos meaning here, you have seen that, right? In the previous, so we had the function of E and it was cos k, right? It is coming from there. So this is periodic. So this is like periodic function, right? So this Brougham zone is periodic. That's why you can flip. I mean, whatever you have this point is same as this point. Meaning it essentially, it is not about only cos. It is essentially saying A is equals to B. We have two atoms, A equals to B. That's what it says. Okay. So now we can do the same. So now, so this band we can flip here, and now what will happen to this? So this is 1. What should this point come? This point. Should this come here? Because this is 1. This is 1. These axes are same, right? So here this is 1. This is 1, right? So this point should come here, and this minus 1 should come here, right? Do you agree? Something like this. And you, so now compare what we derived earlier in the chronic penny model. Exact same thing, right? Okay, so essentially what we have done, so anyway, in the previous class we solved chronic penny using block equation, I mean block wave function, okay, with the periodic boundary condition. That was mathematical derivation. But here, just assuming that band gap opens at the Brougham zone, okay, because of the interaction, and just slightly modifying the free electron, we can get in the same result. So this is the intuitive understanding. Okay? Okay. So now you know like E versus K, this relation, okay? Now, okay, so I mean, in next 15 minutes, uh, you'll appreciate why the essence, okay, or implication of this E versus EK dispersion. Because if you know EK profile, that means you know everything, okay, for a material as a transport engineer or as an electrical engineer, okay? Okay. So before that, just very quick recap. Like, so it is electron. Whenever electrons moving, that means a wave, corresponding wave packet essentially moves. Okay, here I just try to show that wave packet, if I take two wave functions, maybe or many wave functions, it will be like that. Somewhere we'll have positive interference, you have higher intensity, and other places it will cancel. And what will happen? So if this is happening at t equals to 0, as time evolves, so these waves move differently. Okay, because they have this phase factor which is slightly different. Okay, and then you will see this wave packet is forming somewhere else, meaning the particle has moved. Okay, anyway, we discussed already previously. Okay, okay, now we need to know what is a group velocity and how to get that from E versus K. Because velocity is important to find current or electricity. Essentially, you need two things. One is the number of carriers and another is the velocity. Okay. So again, when you are saying number of carriers, maybe you should think about distribution. Okay. Then, so we can also have velocity distribution because different electrons will have different velocities, of course. Okay. But here we will deal everything in K space. So when we are talking about distribution, we'll think about velocity distribution in K space. Okay. Okay. So our job is right now to find the group velocity. So this was the definition of group velocity, if you remember. So this is what we have defined, okay? And that you can also appreciate from this. So I'm not exactly going again, okay, with this concept. So this is how, so group velocity means this entire packet, okay? So yeah, so that's the velocity. And there was another thing called phase velocity, if you remember. So within the packet, so we have this wave function, the velocity of these wave functions, okay? But that we don't care. So what we care, how as a packet it's moving, right? This is what we need to know. Okay. Yeah. And this is like classical. You already know Newton's law. Okay. F is like rate of change of momentum. So in quantum mechanics, so this P is connected to H and K like that. Okay. We just flip it around. So this is what we'll use. So we started with quantum mechanics, but as time progresses, okay, we will see we'll get rid of quantum mechanics. Okay. And we'll use semi-classical equations. But it is not that we'll not use quantum mechanics, but those things will be hidden somewhere. Okay, so because as an electrical engineer, if don't need to solve Schrodinger equation every time, everywhere, right? So what you need is this EK diagram. And my point is, and my job is, if that is given, if you know it somehow, okay, then without doing complicated quantum mechanics, you should be still able to answer and explain things. Okay, we'll now as time progresses simplify things, okay, quite a bit. So that is the first step. Okay, so how EK diagram arises we have seen. We have solved equations, okay, and also I gave you intuitive picture. Okay, different ways of intuitive picture I have provided. Remember we had the thought experiment, and now with the free, nearly free electrons in weak periodic potential. Okay. Okay, now already you know, so, so E versus K relation is given, you know group velocity. Very simple. Okay, right? If I give you a function for EK, you can get Vg, and note that this can be a function of K, right? Okay, that's step number one. So now we'll try to derive something. Okay, let's take a derivative of this guy. Do you agree? This Vg is like ddt, okay? Yeah, so this ddt, and so I can, so if you remember how to take differentiate, d square E by dk square dk by dt. Okay, chain, what is it? Chain rule? I was saying chain reaction. Okay, fine. So now already you have seen this expression, right? This is like force, okay? Fine? Okay? Okay. So that means I can define force. So we have some constant and dv by dt. Okay? So this is nothing but the double derivative, right? That means it is like an effective mass. Okay? So what I try to mean is that we have a particle or we have electron. It is moving with some velocity v. Okay, but electron has a mass, but this is not a free electron mass. When it is inside a crystal, its mass can be different because it will undergo scattering, collision, and effectively with this, because we want to use this Newton sort of semi-classical equation. That's why, okay, rather going into complicated quantum mechanics problem, let's define something which mimics like mass. And that we can easily get from the EK, because EK is the final, I mean, basic thing. If EK dispersion is given, you can know the mass, you can know the group velocity. Fine? You are almost there. Okay? Okay, now let's take some examples. So this is the standard E versus K that we have, and we approximate, right? Like parabolic approximation here and there. Do you agree? That we are taking, and in between we have some variation. Okay, this is like schematics. Okay, so now, so this typically happens in semiconductor. So this type of EK relation is given, then you can plot. Can you plot Vg as a function of K, meaning dE by dK, right? Simple. What will you get? What is the derivative of a parabola? Straight line, and the curvature will be different here and there. Do you agree? Acha, this one is here. Do you agree something like that? So the green one corresponds this one, right? It goes like that. Do you agree? And here for the valence band, I'm just showing with this reddish. Okay. Okay. Same thing here. Why I'm highlighting these places? Because our parabolic approximation holds this place, right? Do you agree? Simple derivative, man. Okay. Questions? Okay. Now, so in between, if you know the profile, you can take a derivative and you can do it, right? But it seems like, so this curve is going and this is, the slope is opposite. Maybe it is something like that. But it depends on the fine structure function. But the important thing, whatever is happening here, because that is coming with the approximation. Okay? Are you with me? Okay. So now this is d by dk, which is fine. Now, if I take one more derivative, then you will get effective mass, right? So again, this band structure or EK dispersion is important because you will see this again and again in this course, again and again. Okay. Now, if I take one more derivative, what do we get? You need to think about first k equals to 0 and k near Brougham zone. So if we have equation of a straight line, then if you take a derivative, what do you get? Constant. That constant will be different here and there. Right? One is, if that constant is positive for this case, this green one, it will be negative, right? For the other one, do you agree? Now it is varying, plus to minus. And in between, we can have some variation depending on the profile. We are not too much interested, okay, at this point, just to show. Okay, now we are we'll mostly be interested around k equals to 0 and k, okay, Brougham zone. Okay, but what do you mean by minus or negative effective mass? How can that mass be negative? Okay, what is the significance of that? Because this kind of bands are always there. What is the significance of that? Okay, so it signifies holes. So we can, okay, I'll explain what it is, but I'm just giving you the answer, MCQ answer. Okay, this signifies hole, a quasi particle. Meaning always there are electrons, but we can think the valence band electrons, or we can treat them, okay, as another quasi particle called holes. How? I just explained. Okay, is this okay?
So the slope is it should be like
Here slope is positive. Flat, yes, because it's constant. Here, straight line. flat, this flat. Here. No,
K equal to 0, it should be
why? Parabola. So this is E equals to k square. D by dk is k, right? Not constant. Yeah, so we are doing near k equals to 0. You take a derivative. So near k equals to 0, E is proportional to k square, right? This is what you have. If you take a derivative, what do you get? If you take a derivative of this, what do you get? So what do we have it here? Straight line?
that way.
No, no. Why should it be the if you take a derivative of this, okay, then you get h by m. That is not h by m times k, right? You have k. No, no. K equals to 0. This value is 0. Yes. K equals to 0. The value is 0. Yeah. So here, that's an important point. As you're saying, k equals to 0. Value is 0. So this point is 0. But this is a straight line. Do you agree or not? Yes, k equals to 0. So here dE by dk 0, that's important. 0. What do you mean? What does it signify? K equals to 0, dE by dk 0, meaning velocity is 0. K is what? What is K? Momentum. If you don't have any momentum, what velocity will you have? 0, consistent. Okay. Okay. So now I can give you linear dispersion. Maybe somewhere if slope changes somewhere in between you will have, right? This type of linear dispersions generally arise in several materials including graphene. Okay, what is the effective mass you have? Okay, so these things are valid when double derivative doesn't blow, but here it will blow. Okay, so this is a question for you. Generally these kind of questions are asked in exams or and interviews. Okay, you think about it. Okay, study. Anyway, so I'll upload my notes. It is the answer is given there. But anyway, you think about it. Okay. So now, so I'll stop this lecture very soon. Just I'll try to give you this understanding. What is like, what do you mean by negative mass? And in like in 5 minutes. Okay. Yeah. Okay. So at 0 Kelvin, we have all electrons in the valence band, lower energy state. Valence band is completely filled, right? If valence band is completely filled, you can think it in this way. You have a water bottle full of water. Can you displace water in that case without, if it doesn't have any bubble? Because whatever electrons you have for plus k, you have same number of electrons for minus k. They will cancel. Plus k and minus k states will cancel. So net current is 0. Okay. So what does it physically mean? It physically means that you have a silicon crystal, you have silicons all. If it is a perfect crystal, so we have covalent bonds everywhere, no bond is broken. Okay, all electrons are there participating in the covalent bonds. Okay, if they are bonded, you can't move them, so net current is 0. So bonded meaning, that's why it is called in valence band. Valence. Okay, is it okay? Now as you increase the temperature, what happens? Some electrons will be excited. So when students are excited, what they do? They protest. They jump also. They can protest in Jantru Mantru. I won't say because if it goes viral some point of time, Jantru Mantru maybe not in India, okay? They can protest in Jantru Mantru. Okay, so they are now excited when they're. So here students will go Jantru Mantru, but here electrons will jump from valence to conduction band. Right? Fine? Okay. So now even at this case, okay, now let me tell you what does it physically mean. So we had these bonds, right? We have these covalent bonds. So as you increase the temperature, maybe some electrons are moved. Okay, some electrons got enough energy, thermal energy, and they are now free from this bond. They are roaming around. They don't care. Okay, they just roam around because they are free. They think that they can do anything. They are called free electrons, meaning these electrons represent an electron in conduction band. Okay, so now we have a vacancy. That vacancy is referred as holes. Just I'm saying, okay, absence of electrons. And every time another electron comes to this place, the hole also moves, right? That means holes move the other direction of electron, opposite to electron. Is this clear? So now we have two resources. One is that the electron which just got free, okay, liberated completely and moving around. World tour probability is going, okay. That is that conduction electron. And still there are some electrons, okay, maybe cannot go everywhere, but maybe can hop, I mean, nearby. So we have valence electron, which can also move. Rather than tracking each electrons in valence band moving, you can track holes moving, like this gap is moving. You can think it in this way. Okay, now this is the electron, so that's why we generally refer the generation of electron hole pairs. So whenever we have generation of electrons, for this context, we also have generation of holes. Okay, is it now clear? Still, will you have net current for this case? You have not applied any bias voltage, no external force, so you won't have any current, right? Why? Because it is symmetric. So here whatever k, plus k and minus k is symmetric, this is also symmetric, okay? So plus and minus will cancel each other, okay? So now we have two types of electrons. So one is, okay, first, okay, there are many things. First one, let's focus near k equals to 0. The reason is that most exciting thing is happening near k equals to 0, okay? So near k equals to 0, electrons in conduction band having positive effective mass. But here in valence band, it is having negative effective mass. Okay, so in valence band, electrons feel like negative effective mass. Okay, that is the consequence, that is the significance. So valence band electrons behave differently as compared to conduction band electrons. Okay, that's what I try to mean. But there are maybe one or two sentences I just add. Now, if you apply bias voltage, then what happens? You break this symmetry. Now, everything is moved. This entire thing, okay, whatever electrons here we have here and there. Suppose we have applied bias voltage along X. So this will move along Y, Ky. Okay, it will be displaced. Now you can see that this positive and negative, like plus K and minus K states will not balance, right? Because it is already asymmetric. That means in that case, you can have current. So this is the definition of current that you have learned. Charge, okay, flowing per unit, I mean moving per unit time. If we have the charge distribution rho, velocity, okay, so we need to integrate. Okay, so instead of having this in integral form, we can, I mean summation form, we can have it in integral form. So this df is important. So q goes outside. Because I mentioned this is distribution, cloud of electrons. When we apply field, the cloud of electron is moving. Okay, so this cloud of electron is displaced. Okay, and whenever we have v, the cloud of electron can have the distribution of electron can have some distribution of v. So you need to integrate it. Okay. So if there are n number of bands, here we have conduction and valence band. If we have n number of bands, you need to integrate for n number of bands. Okay, and then you'll get the current. Okay, so in maybe next class we'll talk about more what this df is. Okay, last one concluding sentence. So here, instead of tracking electrons in valence band, so negatively charged electrons with negative effective mass in valence band, instead of saying that, we can consider holes with positive charge. Okay, then things will be consistent. Okay, so that's the intuitive way of interpreting holes and this. Okay, so with this I conclude that. So I have already written the notes. You can read it. Okay, and then you can explore different books available. Okay. Okay.